Y'all for getting out of bed and showing up on the first slot Sunday morning. This is IDAPython, the Wonder Woman of reversing, and my hope is to help you see how you can automate a lot of the processes that is associated when you're looking at the firmware of microcontrollers and microprocessors. So I'm Maddie Stone, and I am a reverse engineer at the Johns Hopkins Applied Physics Lab out in Laurel, Maryland. I've been there for the past 4.5 years doing mostly embedded reversing, so doing hardware reversing of board-level PCBs, wired protocol reversing, and firmware, and really understanding how all those pieces have to interact, and doing that for vulnerability finding and proof of concept exploit dev. So there, for the past 2 years, I've been leading our reverse engineering working group, which is about 170 people, and yeah, so let's dig in. So the whole point of this and the toolkit I've released is how can you reduce the time when you're reversing all these embedded firmware images, and you can do that using IDAPython. So before we dig in, if you just want to start playing, just want to get to that and not listening to a lecture, it's all available right here on my GitHub. That's where I continue to put presentations, update information, add new scripts, update scripts, etc. So before we dig in a little more, what is IDAPython? So we have to start with, if you don't know, IDAPro is the most commonly used, commercially available disassembler used for static analysis and reverse engineering. And so IDAPython is a plugin that they've provided for that to use Python and script a lot of their API calls. So that's what we're focusing on here, because obviously Python is a well-known language, so let's use it to interact with our databases. So you can see their source code up on their GitHub, and they also have docs available on this website. And so lucky me, we'll talk about this a little more. They released their new version 7.0 last Thursday, or a week ago Thursday, and so they still haven't quite updated all of their docs yet. So the source code is all still based on 6.9.5, and the docs are a merge currently between 6.9.5 and 7.0. So just want to give you a heads up if you head to those and you're like, what the heck? Yeah, we're all right there with you for now. But, so before we dig in a little more, I started creating this presentation, all these scripts, much earlier than last Thursday when they released all these updates, but they're exciting updates. The whole disassembler has been moved to 64-bit, but the implications for IDAPython with this new update, and you should go in understanding this talk for, is they created a whole new SDK and API. Basically rewrote everything, changed everything from camel case, or changed most things from camel case to snake case, moved a lot of things in between different modules, removed some portions, added new stuff, things like that. That being said, they were nice to us. They kept a compatibility layer in there for this version so that most things will still work and not break if you're running IDA 7.0. But for this talk, what you should know going in is that I have not fully tested all scripts for IDA 7.0 yet. I have run them, but I'm not going to say they've been tested on all the architectures with all the processor modules yet. So my goal is to get that done within the next week, to be able to be like, yep, you're good to go, you can expect this behavior. Over the next couple months, and if y'all want to help, it's open source, I want to port it to the 7.0 SDK, and what's exciting is there are some new features we can utilize and leverage with that. But at the end of this talk, I will be doing a live demo on a new firmware image and how to run the scripts, and I am using IDA 6.9.5 for that. But backing up again, why do you care? Why should you sit here? Why did I think I should present this to you? The key point is these were all scripts that I was having to use every day. And when I started looking at these microcontroller and microprocessor firmware images and started trying to understand what IDAPython scripts already exist, all of the resources I could find were based on x86 and ARM, and generally applications or malware analysis. And the key is that that just differs from what we're trying to do when we're reversing embedded firmware images. So that's why I created this, but for background resources, Palo Alto Networks has a great series of blog posts to get some awareness of IDAPython. Alexander Hanel wrote a great free ebook on the Beginner's Guide to IDAPython. But this talk and everything I've created is focusing on the microcontrollers and microprocessors. And while we all need to keep doing more of these microcontrollers and microprocessor firmware images, I don't need to tell any of y'all Internet of Things is making it so we have to keep working quickly as they keep updating images and new versions of everything. And so we just have to get faster to be able to compete. So what are some of these important differences that we got to keep in mind when we are reversing an embedded firmware image instead of looking at, an application? So the first thing we got to think about is, why are we doing our analysis? In applications, that's usually your malware, you're looking for how are they interacting with the operating system? Are they creating new connections? Are they grabbing new data? When we're looking at a firmware image, though, we care about how is this firmware controlling GPIOs, because the only reason this processor exists and this code exists is because it's controlling some physical functions outside of that chip. So that's where we want to focus our analysis, focus on what are they sensing, what is the data that's coming in that they're making decision points off of, and then how are they making the decisions that goes out. So that might be turn on this motor driver, turn on these lights, add power to this system. So that's what we want to go ahead and use scripts to focus all of our analysis right there. We also care about how are they configuring and controlling peripherals or their communications interfaces, what's coming in and going out via serial, CAN bus, etc. Are they using compare captures or PWN modules? All of this is where we want to focus instead of getting bogged down in maybe some of the other support code. So the other thing we're looking at is that when you have an application you generally have a PE file or an ELF file that gives you a lot of information there. Not the case when you're looking at embedded. You've probably just pulled or extracted the firmware and it's a binary blob. So how are you going to figure out what's your code, what's data, what's maybe where does RAM live? How do all these pieces interact? And that's your job to do. Nothing's there to tell you what that looks like. So we need some scripts to help us go ahead and be like, cool, let's define all of this as code, let's define all of this as data, things like that. Another important piece that's different is our memory structures. So a lot of microcontrollers are using Harvard architectures, which means that the instruction and code bus is separate from your data bus. And so how are you going to interact and understand that this code over here is actually reading, writing in the memory over here? Because IDA doesn't always process that clearly. And then you also have a lot of indirect memory accesses, because you might have a configuration table. The manufacturer, let's say, uses this same firmware image across all these different versions, maybe their legacy code too, and instead of updating the code, they just put a config table in there and say, hey, check this value. If it's set, you're going to use these features. If not, you're not. These are your jump tables, things like that. But if we can't see that interaction and the understanding between the code and data, we're kind of screwed. How do we know what's going on? So using scripts to help with that. And then the key point that I focused on in this toolkit was that, every device you open, you may find a whole new processor in there. So by building tools that are specific to a specific architecture, you're rewriting things every time you open a new device. And so how can we take a step back and create scripts and tools for ourselves that can be processor agnostic so that we can continue applying them each time we get a new image instead of having to rewrite a whole new thing based on syntax or memory mapping, things like that. So the approach I took to scripting the reverse engineering process is taking a step back and looking at what are the pieces of things I want a tool to help me automate help me automate and let it do. So the first step is that triage. You got a binary blob. Where do we start? IDA can't find anything. It did no entry points. The processor module doesn't have the full support. Let's get that database to a point that we can actually start doing our static analysis of the code. Then we can move into scripts that help us do our analysis. Where are the key points that we care about? Where are the code that are interacting with the same memory map special function registers? Where's everything that interacts with a port, etc.? The last piece of this is what I sort of just called annotation, which is just helping to label things in your database so that you don't have to keep coming back, recalculating, looking at code that you know is dead, looking at just things that really don't matter. So giving yourself those labels within that IDA database to just really help you keep moving and moving more quickly. So like I said, what do I mean by triage? Let's take a look. So first we've got an OtML AVR firmware image that we pulled straight into IDA. That gold bar at the top means that IDA could not define anything. It couldn't find any code, it couldn't find any data, no functions, and that's after it's run its own analysis process. This usually means it's just because it has no idea where the entry point is, but maybe you don't either, because you pulled this firmware image, but you don't know if you got all of the memory or not when you did a read or things like that. You don't know where your starting point is. So this is something that does happen quite often. As you'll see when then I pulled in a MIPS binary and got the same result. And also a PIC 18. So where do you start from when I can't help you at all with any of these pieces? So the 3 scripts in my IDAPython embedded toolkit, they start as, first, define data as types, which it's super simple, but instead of having to go down a whole block that you're like, this looks like a table, or all of this is data right here, and having to go D, D, D all the way down through it, you put in some addresses, tell it what size, whether it's a byte, word, or double word table, and it will just go through and define all of it for you in one fell swoop. The next one is define code and functions. So this is what can help you, and one of the things that I use first is to go through and just be like, hey, I know this area within my image is ROM. Let's just see what happens if I try and define it all as functions and code. And so this one does use processor-specific regular expressions to say, this is the prologue I'm looking for, this is the epilogue I'm looking for, to do a little bit smarter, and so that you don't just get everything forced as such. And the last one is make strings. When you see a block of area that you're like, this is all strings, don't want to go through again on your own, doing A, trying to do it manually, you can just say, hey, look for ASCII, they should all be at least this long in length, they have these characters, they should end with one of these characters, so let's go ahead and define anything you find that matches those requirements. So you will not use all of these every time you open a firmware image. You still have to use that knowledge of what you're looking at in the architecture to work. It's not like a fully automated framework. For example, define data as types would not work on any of the Renaissance Super H architectures, because in that one, all of their data is just under each function. So you're not going to have that giant block to be like, this is data and this is code. So you still do need to have that little bit of awareness within there. So let's look at this one. This is, I believe, the OtML. And so we are going to just run through how do we run that define code and function script within here. So you go to File, Script, select your script, put in the beginning and ending address, which for me, I just looked at when did it turn to all Fs at the end of the image and said between those boundaries. And now we have, what, 141 functions defined for us that we can start working off of and start our understanding of. Oh, I'm moving quickly. But what is this processor agnostic structure? How do we do this? How do we continue writing and building tools that aren't specific to syntax and the actual chips we're looking at? So the first way that I went about thinking this is all of these came out of the fact that I was writing the same scripts over and over again, but for specific syntax. I was like, okay, I'm looking at C166 now. I can't use my 8051 scripts, gotta switch over. So taking a step back instead and thinking about what in general am I trying to do? Then now what is that smallest piece that has to be dependent on syntax? Is there ways that I can just look at what's around me, look at the structure, abstract out certain pieces? So I really only need maybe 1 or 2 regular expression lines that have to be specific to each architecture going through. And so thanks to Tamir Bahar, he was the one who pointed me in the direction of this IDAPython API call, which gets its get in structure will return the IDA information structure associated with your database. In there they have a processor name, variable. It is valuable though too. And so by using that, the script will automatically look up which processor you're running on. It will check if if you have put in regular expressions for that processor, and then it will just automatically take them and run with it. Before, I have presented a shorter talk of this at Recon in June when I first put together all these scripts, and the user had to go in and comment in and comment out based on their knowledge of the processor. So it's really great, and I appreciated his contribution in making that automated. That being said, when you look at the scripts, I don't have every processor in there because I just add to it when I'm working on each architecture. So if you take it, if you know that you always work with this specific processor, I'd greatly appreciate it if you contribute those 1 or 2 lines of regular expressions in there. But so what does this look like? I don't know if that's big enough for y'all to read, so I'll try here. But this is the starting point of the code for that define code functions we just ran. So as you can see at the top, that is where we get the processor name. Then what I've added in here in the processors I have supported thus far are 8051, PIC-18, Mitsubishi M32R, Texas Instruments TMS 32028, and AVR. So really, that's all you gotta add. A lot of these don't have a specific prologue, so that's where you use the sort of default regular expression, and then just try and figure out which instructions do you generally see as the epilogue, the last instruction, and just put a regular expression in that. If you are more comfortable with strings other than regular expressions, obviously that is a way you can do that too. We got a nice green look now. It's hacked. So moving on to analysis. We've got our database, it's all triage, we know this is code, we know this is data, this is strings, this is RAM, this is where SFRs live, what now? So one of the key points that I was always felt like I was spending so much time in banging my head against my computer was understanding how these functions were interacting, reading, writing memory. And that comes back to what we originally talked about. So let's use 8051 as an example. Since 8051 is a Harvard architecture, to access any memory on the memory bus, they have to use the D pointer. So that memory address is loaded into D pointer, then they do moves, and that's when you can read or write to that address. That means that IDA does not know that you are interacting with that memory address. They cannot create cross-references based on that because all you're doing is moving immediate number into the register D pointer. So how can we see that this function over here, oh yeah, and this one are all interacting with these same groups of memory addresses? So that's where find memory access or find mem accesses comes into play. What it's going to do for you is it's going to look for that regular expression. For us on 8051, it's move D pointer. And then it's going to look at what that immediate address is. It is going to then create the cross-references using the add deref instruction back and forth. So now, let's say you're at a function, you see that it's interacting with that memory address, you double-click on it to see where it goes, if it's already set value or if it's, read-writable, and now you can just do Control-X and see who else is talking with this. Who else cares about this value or who else is writing? And that saves so much time and energy. On another point, though, we also see a lot in these architectures of indirect memory offset accesses. And what that really means, we're getting a whole rainbow of colors. What this really means is that, say for example, on the one that I have at the bottom of this slide, if it's readable at all, is Mitsubishi M32R architecture, which is now you'll find on the Renaissance website since they acquired them, is what they did in this code, since they want it to be adaptable for different versions of hardware, board support packages, etc., is that at the very beginning of the code, they set the frame pointer to an address that's going to be, this is the block of memory this set of code is going to work off of. For others, they just have different places in the image so that they can use different values for calculations, timing, things like that. So everywhere in the code, I kept seeing things like this load or put the value that is at the frame pointer plus hex 4114 into register 1. That really doesn't help me very much as I'm trying to do anything. I had to, so that it turns out the value of this frame pointer was 80800, something like that. So it's not easy math to do in your head to just very clearly see it. And then you also see things such as these add 3 instructions where they are loading a register with that memory address to then access later on. So what this script will do for you is it goes through, it looks for that regular expression that for here I defined it as, you know, an offset memory access using frame pointer, or the add 3 instruction using the frame pointer. And it's going to then first find all of those places for you. Then it will do that calculation of what is the actual memory address. So adding that value of frame pointer to the offset. Then it's going to replace the operand in that instruction so you can just see very clearly what memory address you're actually working with, which by doing that exact syntax, that makes it clickable and everything like that. And then it will create the data references back and forth. And suddenly, you know, so for Mitsubishi M32R, all of their special function registers and ports are memory mapped. So now suddenly I know that, this value at port A is now being read and written by these different functions. And oh look, it's not only one that can set the value that is ultimately controlling this pump system. This one over here is the error case. And maybe I wouldn't have found that before if I wasn't able to say, oh, this is everyone that's interacting with that pin. And that's really helps with all of this time and things like that. And so one other aspect of this is that, thanks for the hydration. So another key point of this is that in a lot of these different things, you're working across segments or external memory and things like that. So how are these addressable? And I haven't added it in yet because I'm still trying to come up with a way that I think would be best to make this processor agnostic. But let's say in C166, they only use the 14 bits of the address. The top 2 say which page you're going to be in, and then you do the calculations and add it. So I've been able to do that for specific databases, but trying and using the majority of this code to do all of that, but trying to work and think about how to make that processor agnostic to help you see when you're working with things like PIC and C166 that have these page pointers throughout. So this is what it looks like. This is my M32R database, and this is going to be really terrible for y'all to look at on the red. And we're going to run this script and watch it change all of these instructions, like watch these 2. Do y'all see my cursor at all? Yeah. So these 2 instructions, for example, are places that you will see changed and altered by this script. And all we got to do is we go up to File, select Script File, select Data Offset Calc, and we're going to put our beginning and ending addresses. I just used it where there was code and looking at where all those F's and zeros are. And then it runs through changing and creating all the data cross references. So now I can just click on it, press Control X, and see who else interacts with that database. And say, hey, actually I want to go to this next subroutine and see what they're doing with it. And I can then jump to the next one and see what else. And maybe one of those I've already done analysis on to help me understand maybe the purpose behind it. And you can go to the memory address, have all of your data cross-references throughout, whether it was an add3 or the actual indirect offset in a load. So what does this look like? How do you actually do this? You've probably heard, and I probably didn't help with my talk about the IDA 7.0, but a lot of people stay away from IDAPython because it is not easy to understand the docs, and there isn't a lot of documentation on it. But the reality is that the majority of all the code written is general Python. The only time you need to pull out one of those IDAPython specific calls is when you're actually interacting with the database. And thankfully, that can be pretty simple. So every script, I think there's 8 now in the IDAPython embedded toolkit, is less than, I think most are less than 40 lines. I think every single one is less than 100 lines. So it's not a lot of code going through there. This is every IDAPython call in that data offset calc right here. So the rest of it, the majority of it, is regular old Python. And so when you're looking at those IDAPython docs, what I need to get information, and then I want to set stuff. So to start, the very first thing I got to do is I need to go and find those operands to see if it matches my regular expression, to be like, ding, 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 here's your indirect offset memory access. Let's go ahead and change that and process that. So we use the get operand command here. And that one just tells us which operand we want from that instruction. Then, if, say, we've run our regular expression code, it matches, we know that we have an offset in there, and we just did some processing to find out what that offset is, we just move on to checking if it's negative or positive so we can actually do the calculation. And so that's what we do in the if else statement right here. And then this op-alt is how we actually change the operand and how it's being displayed. So we can get rid of how the rest of the instruction says, you know, the at, the offset, comma, FP. We just say, here's your memory address. Take it. I don't need to look at the other stuff. Then we just use add deref to create that new data cross-reference. So from the address we're at to the new memory address we calculated. And then it takes a type, which I just use DRT, meaning text, because otherwise we would have to get into more processor-specific stuff to understand whether it's a read or a write. And hey, for me right now, all it matters is that I can see them. By looking at it, I was able to see the reads or write. But if you want to add that in, hey, I'll take it. So the next step we take is we're going to create a comment if we wanted to, instead of replacing the actual operand. And we do it with the same syntax as how IDA would usually display it, so it's clickable and they know that to take you to that memory address. And finally, the only other IDAPython call we need in this whole script is next head, which gets us the next address we want to start looking at and processing as we run through the data range we inputted. So as you can see, you really can do a lot based on your previous Python knowledge without having to get into the IDA-specific API calls. So finally, we got through some analysis. What do we do with annotate? How can this help us a little bit? One of the key things that sounds super simple, what's really helpful, is a script that will run through your whole code base and check whether or not functions have cross-references to them. So no, this will not work for any architectures that do a lot of indirect function calling, but for others that really don't have that capability built into their instruction set, you suddenly know if there are blocks of functions that are used for maybe legacy code, another board. Maybe they have code that's developer only built in, and it just helps you really highlight and understand what you're looking at. So what this does, it runs through the whole thing, finding any code with cross-references, then it iterates through those, going down. So let's say you found a function that has no cross-references that calls 4 other functions. Of the 3, that's the only place they're not called, so meaning those could never be called either. It keeps working down the chain. So you don't spend time, wasn't me, that probably was me. Damn computers. Who needs them? Oh, that was Nathan.
Is it back up?
There. Thank you. So let's. Oh.
It looks like it's up. Your phone,
Yep.
That should keep it from sliding. I think that's what the problem is.
Okay, thank you. Thank you very much. So you can now know what's dead code or possibly dead code or not. Goes through, it can both write it to a file for you so you can parse that if interested, but also for me, in this script, it will by default add a prefix to each function name that just says no cross-refs. So then as you're looking at a function list, you can just be like, cool, these don't have function cross-refs. I'm not going to be pulled into a rabbit hole down there unless I really mean for that to happen. The next one really gets into what we talked about of we really just care a lot about how they're controlling and sensing GPIOs. So they use the regular expressions for each architecture of how does IDA display those special function registers or ports whenever they're interacting with them. Searches for those in function codes in your instructions. One will list them in a CSV file, so if you like to do processing and understanding that way, but it will also, if you would like, it gives you the option as it runs in a dialog, prefix each function with just that port number that it's interacting with. So we'll see it in the demo, but that really helps to understand and be like, cool, this is the one that's actually reading and writing this port right here. Yeah, and then identify operand locations. I added that one in by just a request via Twitter from someone who wanted to just track on some architectures that have the stack pointer and the frame pointer just being used within the function. How can they quickly see each of those places? So this script in general will just search operand locations for you within the address range that you give it, and you just put in whatever regular expression you're looking for. So really just sort of a search type of thing if you're not wanting to use IDA's built-in search capabilities. Oh, this is the wrong one. Oh, there it is. So this is every IDAPython function that the whole toolkit had to use. So this gets back to it that the fact that it's IDAPython, lack of docs, shouldn't be something that's scary. That being said, these all are for 6.9.5, and I think almost every single one of them has now changed in 7.0. So the point of the slide kind of has changed a little bit. But I'm planning, when I was trying to learn IDAPython and how to leverage it for my needs, what I really focused on was just where are the gets and where are the sets. And in their toolkit, they generally use the word make for anything that's a setter. And so when you focus on those pieces, it's much, much easier not to get bogged down in all the other calls that people use for more robust plugins and interacting with the full IDA toolkit. Because we really are just processing a lot of that textual disassembly representation to us to be able to help make our needs much easier. And so in 6.9.5, when you go to the IDAPython docs, you'll see, I'm probably just making up this number totally, but it feels like it's like 40 or 50 modules listed there for you to start looking at functions in. All of these, except for the 3 that have asterisks on them, were found in the IDC module. So you really don't have to get pulled into everything. Just start your search for what you're looking for at IDC, and then you can move up from there. But so what's next? I'm going to continue adding things. There are more features. I've written a script that will look for and process interactions or configuring and controlling different peripheral modules like I2C or UARTs, all those different types of peripherals. It kind of broke with the update, so I'm working on getting that fixed enough and tested again. And So I think there's more of these triage processes we can automate, build in together so it doesn't have to have so much user interaction. I think it would be good to have more understanding scripting associated with different segments that are built in, especially when, you know, there's sometimes for different processor modules people have built into IDA. They do RAM over here, they do SFRs over here, they split the ROM up into different ways. So how can you understand that in a processor agnostic way? Check, we did do automate architecture selection for scripts. The one thing I'm still working on is how do you understand which device of the processor you're trying to do. Currently, I have one of those choosers that you have to select it again, say for 8051, is it C515 or 80C52 or something like that, because those do show your special function registers differently. So I've been trying to work through a way to automate that piece of it. And just other manners to display information, because we all sort of are very particular, is a nice way to put it, about how our databases work, show information, things like that. So what other options and cool ways can we come up with? But really my whole goal here is that, you know, there's so many tools and processes and brainstorming going on and creativity that's happened on the x86, you know, ARM application and malware reversing community. How do we continue building that up for these microcontrollers and microprocessors as, say, adversaries move into doing more exploitation over there, and we just have to keep getting faster and more adaptable and more flexible. So hey, it'd be really cool if someone wanted to come up with a whole automated framework that I can sit in and listen to next year. But with that, I'm going to switch over to a demo. If I can figure out how to get it up on the screen. Let's see. Hold on. Where is this? Computers. That's the wrong button. So we'll see how this looks on the screen. But I have this just straight read off of a PIC-18 chip. It was read off of, you know, via a debugging to get it off, and now we have the binary blob, but this time in a hex file, but still binary blob. So what do we do now? When we load this into IDA, let's see what we get. Where did I put my notes? So we have our hex format. We're going to go to microchip PIC-18C. This is what I mean when I said that we haven't automated the device name yet, but for this one, it's 4525-ish. And, oh, that's terrible. Let's see. Tried to make it big to see if that would help with reading, but okay. And then let me zoom in so y'all can see what this knows on the top of the screen. Oops. So that's a little too zoomed in. So what we can see is it was able to define a couple of different segments as shown by these black bars at the top. We have a lot of code that it says is code, but it doesn't quite know. The blue, oh, that's joy. Oh, that is cut off. Okay. Thank you. Because I would have just kept talking for myself. That didn't work. Hold on. Okay, well, so trust me that the top bar tells you that there's some code, there's some undefined stuff in there, all sorts of good things. So what I'm just going to do, since it's just sort of broken up, it found some function somewhere, it doesn't. I know that based on going through hex view, right here on this border, that's where it starts with a whole string of Fs. So to just try it out, I'm going to run the define code and function script just to see if it just couldn't find the entry point, and so didn't get everything at the start. So what I do is I put my starting address. I just want it to start at the beginning. Instead of going all the way to the end, I'm going to use that address that started this string of Fs, which is 6E44. And I'm going to go ahead and tell it to set everything as unknown first, and just so it doesn't get caught up in what it thinks might have been previous function boundaries, since I've done no analysis yet. And so as it runs through, it actually found and declared almost everything at that top bar as functions and code within there. But when I start at this top and start looking a little closer, say, at this function, what I see is that there's actually a large block of Fs within here. And this gets back to that being particular types of things with your database. And I don't like to have code blocks shown as code if they're actually not. So this is a case where I'll just go ahead and take the defined data as types piece of this and say, I just want that all to show as some word section. So that address is 0x1e going all the way to 0x2000, just so I don't have to look at a bunch of knobs. Because looking at Fs is so much better. So once we've got here, I really want to know, can I filter down some of these functions? So let's go ahead and see if there are any that this script says don't have any cross-references to them. So I'm going to grab the label function with no cross-refs function in there, which this function I didn't mention earlier. It also has a little list if you want to put a couple of function start addresses at the top, because, for example, your reset loop is going to have no cross-references, but that's kind of the whole point and really needed to start everything throughout. So in order to be able to do that iterative process of working down the paths, you have to have the starting point. So I just put in here my reset vector address to ignore when declining cross-refs and 2 interrupt vectors. So when we run it, I'm just going to say start at the beginning, go to the end, and look, we now have 1, 2, 3, 4, 5, 6, 7, 10-ish. We'll go with that. Functions that they're saying have no cross-references. We don't need to worry about getting caught in any of those. Now the next thing to just sort of work and get through some analysis is I will run the identify port use locations. It's going to grab my regular expressions for me off the bat. Again, I can just go from beginning to end because it's looking for code anyways. And then it asks me for a place to where do I want to save a listing of that file that I create, all the addresses that use it. And would you like to append, I guess that should be prepend, not append, but anyways, append a prefix to the beginning of the function. Yes, please. And now I can see right here, it's labeled it as 1, 2, 3, 4 functions are interacting with port B. Let's see if we can find it. I could also look up. That's a bigger function. Oh, that's a really big function. So I might not find it in there. But so the same thing that's written. Oh, here. Here is, this also lists every single instruction for me if I wanted to then do some textual processing on that of here's the address, here's the types of instructions that are working off of these ports. So that's a little demo. Thank you all for getting up and out of bed super early, and do you have any questions? Go ahead. So I haven't run into that trouble yet. Oh, the question was, since using for finding prologues and epilogues, and you're based on the syntax versus the opcodes, have you run into trouble with that syntax being updated across processor modules? And I haven't yet because in reality I haven't seen processor modules updated that regularly, and that usually they're using pretty similar to the straight syntax of the instruction set. Are there any other questions?